Okay, thank you. Thank you for coming back after this long week of great conference and great talks. I'm going to talk to you about invariance principles in the design of neural networks because, well, I'm kind of a newcomer to the field, and I want first to start with some of the difficulties that I met when I wanted to play with neural networks on my own computer. And so let us start with two examples. I wanted to do modeling of text, of structured text, and I wanted to learn that with a recurrent network, and I was a bit naive at the time, so I expected to be able to learn very complicated structures in 5 minutes on my laptop. Okay, this was a little bit optimistic maybe, but let me just discuss two examples. The first example is synthetic music notation in LeCun format, for those who know it. So you have several layers of structures in this example. The first structure is purely syntactical. You have a pitch name, a duration name, for example, C for C, and 2 for half note, 4 for quarter note, etc., etc. The pitches and durations are separated by white spaces, and you have a bar symbol for the end of each musical bar. So that's the lower level structure. You have a higher level structure, which is, this is actually a waltz. If you count the durations of the notes in each bar, you'll get that you get 3/4 notes. For example, in the second bar here, you have, you have, where is it? You have a dotted quarter note, an eighth note, and a quarter note, and that makes three beats. So that's a higher level structure. You have an even higher level structure, which is harmonic constraints. So in each musical bar here, I put a hidden variable which tells that all of the pitches in the same musical bar must belong to the same perfect chord. For example, in the second bar here, you have an F, an A, and a C, and that's a perfect chord. So you have only a finite number of possible combinations. In the third bar, you have a G, a B, a G, and a D, and that's all these pitches also belong to a perfect chord. And then there's an even higher level structure hidden here, which is transitions between the harmonies in each bar have to follow a prescribed pattern. For example, after a bar in which you have a G perfect chord, you are more likely to have a bar with a C perfect chord. So I wanted to be able to discover that in a few minutes on a standard laptop using a recurrent network. So the second example, which is a very important structure in natural languages and also in programming languages, is nesting. So here you have the alphabet, except at some point I insert a subsequence, and the subsequence is just the digits in the standard order, and inside the subsequence, I nest a sub-subsequence, which is just a random sequence of uppercase letters. Also, I made a difference. I use uppercase for the sub-subsequence and lowercase for the main sequence, which helps a bit, actually. So learning that is kind of difficult because you have long-term dependencies after the sub-block. So you see here A, B, C, D, E. And you have a long sum block, and you have to resume at F after E. So that is difficult to learn. So example 3 and example 4 are two very classical examples for long-term dependencies. So the first one is long-distance XOR. You have a string of random bits separated by white spaces, except that 2 of the bits are marked with X symbols. And at the end of the line, you have the XOR of the 2 bits that come right after the X's. So in the first line, you have X followed by 1 and X followed by 1. So the XOR is 0. So at the end of the sequence, you have equal 0. And the next line is similar. And the fourth example is a classical, the classical textbook example of something that cannot be learned by a Markov model, which is the ANBN example. So you have a sequence of A's, and you have a new line symbol and a sequence of B's, but the constraint is that the number of B's is equal to the number of A's, which requires memorizing things. So this last example can be treated, for instance, with LSTMs, but it takes quite some time. And so these are 4 basic examples that I expected to learn very quickly using a recurrent network. So I started just by taking one model. So here's one possible model, one of the first I tried a few years ago. At that time, I thought the model was new, but it happens that it was being published at the same time. So it's a gated recurrent neural network, and you have in which the transition weights depend on the last character that you read. So the hidden activity at time t plus 1 is equal to an activation function, for instance sigmoid, or you can use hyperbolic tangent, of a bias plus an input that depends on the latest character x that you read in the sequence, plus some transition weights, and the transition weights depend on the last character. So the transition weights wji from unit j at time t to unit I at time t plus 1 depend on the latest character that is in your sequence. So this is a nice model, and using this model, it's very easy to specify weights that reproduce each of the previous examples. You can just guess the weights from the example. If you build it yourself, it works very nicely. But if you want to learn it, it's more difficult. So I started playing with this. You can learn this with standard backpropagation through time. Well, you could also do an extended Kalman filter, but this is more computationally intensive. So it would only work for small networks, but with backpropagation through time. And then the performance is kind of disappointing. So I started to think more about this example, and I made a very stupid remark, which is that in this model, the bias is redundant, because at each time you only have one active character x. So you can actually remove bi and merge it into the row ix. So you can just substitute, add bi to each row ix for every x, and just remove the bias. So you get a simpler code. It's simpler to train, maybe. It's simpler to program, certainly. But it's the same model class. If you can represent one thing with the bi, you can represent the same thing without the bi. And the surprise is that the performance is different. It's somewhat worse. So what I did is I put back the bi inside the program, and I started to wonder, maybe I can do the reverse thing with the wjix, because going from row ix to row ix plus bi is equivalent to separating one quantity that is added independently of x plus a specific contribution for each different x. So maybe I can split my weights wjix into a basic weight that doesn't depend on x plus a specific weight for each character x. Again, if you do that, you just do a substitution, but it's the same model because you can do the converse transformation. It doesn't change anything. But again, you have a different performance. It's a little bit better, not much, but it's significantly better. Okay, so at that point, I started to get a little bit annoyed because I did a lot of this little parameter shuffling, and I ended up with 20 versions of my program on my laptop, each with slightly different equations for exactly the same model, and all had slightly different performances. And I started to wonder, can we do this systematically? I mean, for a newcomer in neural networks, this can be a real hassle, actually, just finding the right variables. So since I'm a mathematician, I wanted to understand what's going on, and so I took a simpler example. The simpler example is an ordinary feed-forward neural network, and with a sigmoid activation, say, and you have this bias, and you have this sum of incoming activities from other units in the network. So intuitively, I started to think, well, the bias has to balance a sum of n weights. So maybe each time you change a little bit the weights, the bias has to balance that change, and so maybe the bias will be n times larger than the typical weights. So this suggests a simple change of variables, which is to write that the bias is equal to n times normalized bias, if you want. So I just tried this substitution. So you get a new model, or actually you get a new equation for exactly the same model, because it's exactly equivalent, but training is not equivalent. Training, if you replace the bias with n times the bias, it's equivalent to multiplying the learning rate by n squared. Why n squared? Because the gradient with respect to b prime is going to be n times as large, and so your update of b prime is going to be n times as large with backprop, and then the real bias is n times b prime, so that makes n squared. And this is not compensated by adagrad, because adagrad will set the gradient to size 1, but it will still be a gradient for b prime and not a gradient for b. So so you get this scaling problem for the different variables, and adagrad is not fully satisfactory. It doesn't solve it fully. So I played a little bit more. I noticed that scaling the biases by square root of n seemed kind of reasonable and gave good performance. Maybe because you have, if you apply the central limit theorem to this sum of AI times W, you get square root of n as a standard deviation. Maybe not, I don't know. But still, you would want something more systematic. So I considered an even simpler example. Imagine that you train a network to do a handwritten digit recognition. I know a lot of people here do that sometimes. And you have trained a network to recognize black and white digits. How to turn it into a network which recognizes white and black digits? So it's very simple. You want to, the activity is to stay the same. If you have input x and you replace the input x with 1 minus x, so you want to guess new biases and new weight connection values that realize this substitution, and the solution is very simple. You just reverse the weights. But for the biases, it's a little bit more complicated, because if you use sigmoid activation function, for the new biases, you get a mix of the old biases and the weight terms. And that results in a gradient step over W prime and B prime, which does not correspond to the original gradient step on the W and B. So backprop or any other algorithm like adagrad or msprop, things like that, will not be invariant to this substitution. So it means that training on black and white data is not equivalent to training on white and black data, and this is a well-known phenomenon. On MNIST, you have a big difference actually with sigmoid activation functions. You really see the difference. And of course, I started mentioning that to several people, and I got two answers. First answer is, why do you use sigmoid activation function? Just use a hyperbolic tangent. The second answer was, of course, there should be a difference, because activation 1 means that you have a feature that is present, and activation 0 means you have a feature that is not present. So you should not treat 1s and 0s in the same way. So you should not have this invariance. So there were kind of contradictory answers. And so just to give you an example of the difference, this is a stupid neural network that it's an autoencoder with no hidden layer. So you just have an input layer, and I put x on the input layer and a direct connection to an output layer, and I want to learn x from x. So it's just a bunch of perceptrons, if you want. And it's very clear that when there are more ones on the input, training is faster. So here you see the difference. The red curve is when you have more zeros, and the blue curve is when you have more ones. And actually, you can compute the ratio exactly. In that instance, the speed of training is exactly proportional to the number of ones in the input. Exactly proportional. So that kind of bothered me. And you have a similar phenomenon if you go to from sigmoid activation function to hyperbolic tangent. You also have this change of weights and biases, and once more, just as in the previous example, the weights mix with the biases, and so this is one reason why the gradient descent, the backpropagation on the new weights and biases is not equivalent to the original backpropagation. And of course, if you want symmetry with respect to the inputs, the hyperbolic tangent behaves better if you want the symmetry. Okay, you can solve some of these problems by normalizing the inputs but that works only for the input layer, or by centering and normalizing all the activations inside the network. But so that solves part of the problem, but not all. For example, it doesn't solve applying a scaling to some parameters, like multiplying the biases by square root of n. This is not solved by normalizing. So not even all a fine change of variables that you can do are solved by these kind of tricks. Okay, so this I call model rewriting. When you're a programmer and you have several ways in which you can write exactly the same model and you get a different performance in the end, you're kind of annoyed. So I'm going to go back to any kind of recurrent neural network for text, and I really tried a large number of model rewritings, just some stupid changes of variables, and I tried to observe the changes in performance, and this is really annoying at some point. So you have two strategies. Either you try to identify the best variables. So you can try to design a model such that the gradient descent using the variables in your model behaves well. And I think LSTMs do that to some extent. You try to identify exactly the right variables which will solve the exploding gradient problem or whatever. So that is one possible strategy. And in some application it can work very well. Or you can try to use a learning algorithm that is insensitive to any kind of model rewriting within the same class of models. Of course, you are not going to convert a linear model into a nonlinear model, but given a model, just doing a change of variables, a change in the way you write the parameters shouldn't make a difference. And so such an algorithm is called an invariant algorithm. And if you look in the literature, this kind of problem has been solved more than 25 years ago, and the standard answer from the literature is to use the natural gradient, introduced especially by Amory using the Fisher metric, which dates back to 1945, I guess. But the algorithmic cost is huge. You can only use that if you have a small number of parameters. The algorithmic cost, if you do it online with SGG, is the number of parameters squared times the dimensionality of the output of your network, which is a lot. Except, so you can use this only for very small networks with a very small number of parameters, or in situations where your number of parameters is actually much smaller than the size of your network, which is the case, for instance, for convolutional networks. Because then the cost of the natural gradient is going to be negligible compared to the cost of just doing the forward and back propagation passes. Okay, why would you want an invariant training algorithm? First, it's more easy for the programmer because you don't have to identify exactly the right variables. You rely on fewer arbitrary choices while programming. You avoid model rewriting, and you avoid magical numbers like this extract from an excellent tutorial on neural networks from the 90s. Often you get better performance, not always, but often you can get better performance and faster performance especially, and you get performance transfer. If you have an algorithm that works well on one data set, you know that it's going to work just as well on any class of transformations of this data set. And that's kind of important because we all know that it's very easy to find one data set for which any algorithm kind of does well. And if you have some kind of invariance, you know that the reported number in tests in the articles get kind of more significant maybe. Okay, so now I'm going into the math of why all of this happens. So imagine that you train a loss function by gradient descent. Backpropagation is just gradient descent on the parameters of the network. And so you update a parameter with the parameter theta at time k plus 1 is equal to theta at time k minus some learning rate eta times the derivative of the loss function with respect to the parameter. And let us try to rewrite this in an equivalent way. So we know that gradient descent is the shortest path downhill. So what does it mean to be the shortest path downhill? It means that the parameter theta at time k plus 1 solves an optimization problem. You want to decrease the loss function L of theta as fast as possible in a downhill way. That means you do not want to move too much from the current value theta k, and you want to get the best value in the neighborhood of theta k. So this is equivalent to this proximal operator. The equivalence is at second order in the at first order, sorry, in the learning rate. And now you see that you solve a minimizing problem on the loss function subjected to not moving too far from the current point. And of course, this depends on what you call moving too far. So if you change the norm, if you change the definition of the norm, you change the direction of steepest descent. And so usually we all take the norm to be the Euclidean norm. We take some numerical representation of theta. We say theta is a bunch of numbers, it's a vector, and we take the Euclidean norm on that. But this depends on the numerical representation of theta. Even if you do a scaling of some components and not other components, then you're going to change the direction of the shortest path downhill. So just if you try to decide how much to spend on a house based on the surface of the house and on the price of the house, it's going to make a difference whether you express the surface in square feet or in square meters, and the price in euros or dollars. And if you do the gradient descent, you might really end up with a different local optimum, like a small house in the center of the city or a large house in the suburbs. So just because you can really end up at a different local optimum just because you scaled some components of the parameters. So that's a non-trivial problem, and each time you use a gradient, you should think about that, just scaling. Of course, you can help a bit by normalizing, whitening, etc. This helps a bit, but it doesn't solve everything. It doesn't help with all the kind of parameters of model rewritings that I gave in the introduction. Okay, so the solution to this problem, if you want something that is invariant, that doesn't depend on the numerical representation of theta, you should use a norm that depends on what the network does, rather than how you represent the parameter as numbers. So here's an example. The natural gradient defines the distance for the shortest path downhill, defines the distance as the difference in output generated by theta and theta prime. So the distance between two parameters, theta and theta prime, is by definition the KL divergence between the probability distributions that you get on the output when using theta or theta prime. And so the natural gradient, as I said, is not very scalable. So my goal here is to build such norms in a scalable way. So the norms I'm going to build are going to be Riemannian matrix, that is, matrix such that the norm of a change of parameter delta theta is given by a positive definite matrix that depends on the current value of theta. And if you compute the associated shortest path downhill, using this norm, you get that the gradient descent is given now by the usual gradient descent with a multiplication by the inverse of the matrix, defining your metric. Sorry about matrices and metrics. This is how it is. And in the case of the natural gradient, the matrix M is the Fisher information matrix, which is kind of a full matrix of dimension n, and so it's too big to deal with usually. So let me just describe two possible strategies to build invariance norms. So the first obvious strategy is to try to scale down the natural gradient defined by the Fisher information matrix. And so this has been applied since a few years. So we had a very nice talk this week by James Martins trying to work with this. And there was some work a few years ago by Nicolas Leroux and others using a small rank reduction of the Fisher information matrix, but unfortunately, using a small rank reduction breaks all the invariance properties. So that doesn't work. You have to do something else. So another strategy to define a metric, an invariant metric, is to try to start with a metric on the outputs and try to push it inside the network, layer by layer, so kind of backpropagating the metric. And this is related to backpropagation with square weights, and especially the diagonal Gauss-Newton approximation, which was already used in the 90s, except that if you keep only the diagonal, once more, you break all the invariance properties. So you have to do something more than just keeping the diagonal of the Gauss-Newton approximation of the Hessian, if you do that. And of course, if you do a blockwise thing, you get algorithmic complexity that is too high. So I'm going to skip this. So just the general framework for building invariant metrics is to decide that the activities are not numbers. They live in an abstract topological space that is diffeomorphic to real numbers, but you don't know the exact correspondence. And if you can express your algorithm in that setting, in the setting of abstract manifolds, then your algorithm is going to be invariant with respect to the actual parameterization of your manifold, with the actual numbers that you use to encode your manifold. So, and the usual backpropagation, the usual gradient descent is not invariant, is not well defined in this setting, because if you have an abstract manifold, actually the gradient is not a tangent vector, is not a change of parameter, it's a function that eats a change of parameter and returns the change in loss. And you have to somehow convert that into a change of parameter. But you cannot do that into a unique way in general. So how to define useful norms on change of parameters? So if, I just remind you, if I can define a square norm for parameters, I can define an algorithm, I can define a shortest path downhill. So let's do a first try. Let's start at a current value of the parameter and apply a small change delta theta in theta. This results in a small change of the outputs of the network. So imagine that you have any kind of distance on the outputs. You can define the size of the change of parameter as the average size of the change in outputs induced by the change of the parameter. That's a possible definition. So you can do that. This implies no coordinate choice, so it's fully canonical, it's invariant to everything. I didn't require any numerical representation of my parameter to define that. And this is actually the same as the Fisher information metric. So, thanks for trying. Let's play again. We need something simpler. So the second try is to just do this layer by layer if you want, or unit by unit. You can also do this in a recurrent network. So imagine in full generality that you have a variable x, such as one of the parameters, and the variable x influences variables y and z. For example, a unit might influence 2 units. And I'm stating that from a metric on y and z, you can build a metric on x, just by setting that the size of the change in x is by definition the size of the changes it induces on the dependent variables. So you can somehow backpropagate a metric, and this has been known for a long time, not in this vocabulary maybe, but this idea has been known as backpropagation with square weights. It's very much related. So what you can do is start with an output, a metric on the outputs that is defined by the user, say, and you can backpropagate it to the whole network and then to the set of parameters of the network. Since I didn't use any coordinate system, this is invariant with respect to reparameterization of each unit and the reparameterization of each of the parameters that influence a given unit. It's not going to be invariant with reparameterization that mix parameters of different units. But this still covers all the examples of model rewriting that I gave in the introduction. So as I said, the matrix that computes this metric can be explicitly computed in an easy way. You get an online or stochastic gradient version by updating the metric more slowly in a smooth way. You can adapt that to recurrent networks. Okay. And the computational cost of the resulting gradient descent is still linear in the number of units, but it's quadratic in the number of parameters at each given unit. And so it's suitable for sparsely connected networks with a small number of incoming weights for each unit. Later on, I will discuss reduction to linear in number of parameters instead of quadratic, but right now, let me just give you an example. going back to the original problem at the introduction of this talk, so this is the alphabet with nesting example. You remember A, B, C, D, and I had a nesting sequence of numbers. So this curve is fairly typical of every curve you see in every talk in machine learning. You have the curves before, you have the curves after, and the curves after are better. So in blue you have a traditional RNN train with not naive backpropagation, but backpropagation with adapted learning rates for each parameter. And in red you have a Riemannian training. And so you see that you come very close to the true entropy of the model. And you come there much quicker. So on the x-axis in this graph, this is computation time. This is not number of epochs. This is really computation time. And if you look at the scale, you see that to reach a reasonable value here, I need something like 40 seconds, which is less than 10 minutes. So this really works on a laptop. You do not need a GPU or anything. So this is the synthetic music example. So you do not get everything here. You get all of the deep nested structures except the topmost one. Maybe I should try a larger network there. But still, it's much better than just a non-Riemannian training, and it's much faster as well. So this is for the A and B N problem, and here you see that there is a huge difference because the basic RNN doesn't get it at all. And here you have a list of various models and various training methods. And what's interesting is that basically any invariant training algorithm with any model does better than any non-invariant method with any model. And here I included LSTMs. You see that performance isn't so good, but I think this is mainly because LSTMs take a long time to train, and I used a short time window. So I also tried this on MNIST. It's not really useful because on MNIST you get much better performance on the training set, but comparable test performance and can overfit sooner on the train test. I think this is just because there is nothing left much to optimize on MNIST, maybe. Still, what's interesting is that you can get reasonable test performance on MNIST a bit faster and with smaller networks because you get a better optimizer. And so if you use a network with fewer parameters, you can go faster. The interaction with dropout, so since I have another fitting problem, I tried dropout. The interaction with dropout is kind of not satisfying because dropout requires smaller learning rates, and so you lose much of the speed up. And also dropout breaks invariance because you set activities to 0, and 0 is a special value. It's not independent of the numerical representation. But so dropout is not the only regularization strategy, and so variational Bayesian variational inference is another one, and this method interacts very, very well with variational inference because there is a deep relationship with the covariance matrix that you learn in Gaussian variational inference and the metric, the Riemannian metric. We'll see that in a moment. So here is just a graph of what you can get on NIST using a network with fewer parameters. So here's a sparse network with only 50,000 parameters. And in purple, you have backprop. In red, you have the Gauss-Newton method. And in green, you have one of the Riemannian methods. And again, the horizontal scale is computation time. So you get some speed up, but you do not get better performance on MNIST. So here, you remember I had this quadratic dependency on the number of edges for each unit. You can reduce that by using so-called quasi-diagonal matrix, in which you keep only the cross-correlation between the biases and the weights. But you treat different weights from different edges as independent, but you keep the correlation, the scalar product, if you wish. You keep the correlation between biases and weights, and you get a smaller invariance group. You lose some of the invariance properties, but you still keep enough invariance properties to cover all examples of model rewriting that I mentioned in the introduction. So, just to give you an example, you have this diagonal approximation. You have the diagonal approximation of the natural gradient that has been around for a long time. It's related also to Adagrad. You have the diagonal approximation of the Gauss-Newton Hessian, and you have this quasi-diagonal matrix that just take the diagonal approximation plus a few well-chosen non-diagonal terms in the matrix, and that can really make a huge difference. For example, here in red you have adagrad on MNIST again. In blue you have the diagonal approximation of the natural gradient, and in green you have the quasi-diagonal approximation of the natural gradient. And so just a few non-diagonal terms into the matrix, if they are well chosen to ensure invariance, can make a huge difference. So invariance for Bayesian variational inference, I'll skip that because I don't have time, but so in that case, you're searching for a parameter theta bar, an average parameter and covariance matrix of a parameter in search space. And if you use a diagonal covariance matrix in one parameterization or in another parameterization, this is not even the same search space. Before we had the same search space with a different search algorithm, with a different gradient descent. Now we have a different search space because diagonal C for weights and biases for sigmoid is not the same as diagonal C for hyperbolic tangent. And so that works, and there is an easy solution to that for variational inference, which is to use the covariance matrix to update the learning rate, to use the covariance matrix to update the covariance matrix. So this is just a simple difference with standard variational inference training, and these are the equations that also appear in the Kalman filters. So you can do variational inference with at least, I recommend a quasi-diagonal covariance matrix. This is very cheap to do, and it helps. And last, I want to mention invariance with respect to time warping. Because if you want to treat time signals, sometimes you can have something that happens more slowly, like if I'm talking very slowly or very fast right now, and this shouldn't have an impact on training. Like if you have a nesting phenomenon and the size of the nesting subblock is variable, that shouldn't be a problem. So if you take this as an axiom and you work out the invariance, so you have to go first to continuous time to understand what's happening, and you see that if you do a time warping, that amounts to scaling the derivatives of the activations by a variable parameter that depends on time, and that has to be learned. And if you go back to the discrete time, you get that if you want your model to be invariant, to be robust to time warping in your input signal, you have to get a leaky and gated evolution equation. So of course you still have to learn this scaling of the derivatives of the activation. So you scale not the inputs, not the activations, you scale the change of activations, GT. GT scales the change of activations between t+1 and t. And being gated and leaky is typically something you have in LSTMs. And so that might be one possible explanation for the good performance of LSTMs, except here, if you take invariance to time warping as an axiom, you get a slightly different model, and so maybe this is really something that I would like to try at some point. Okay? So in conclusion, I hope that I have convinced you that these invariance considerations are not only things that mathematicians think about, but that have no practical consequences. They deal with very concrete problems that you have as a programmer when you try neural networks for the first time in your life, and they can really deal with smaller running times if you do them well and better optima. And it's related to variational inference. It's related to invariance with respect to time warping. And we are currently trying to package this with Gaëtan and into a library that you could use without knowing anything about Riemannian geometry. Thank you.